off. Chalo. See this one, beta. Ray optics as a limiting case of your wave optics. And under what condition we can make an assumption that wave optics can be applicable as of your ray optics. What is a ray optics application right now? Ray optics, you know that light always travels in a straight line, isn't it? Whereas in wave optics, we talk about the wave light ray like a bending or way in the form of a wavefront. So before we go for the limitation, let us try to define the two terms called as of your Fresnel's distance and Fresnel zones. So Fresnel distance lo mana em cheppunamu source and as well as of your screen are very nearer to each other. Avuna kada. Alanti condition la, if I am taking a parallel beam of a light of wavelength lambda which has been incident on a slit, and I'm passing through the aperture. If I talk about only the ray optics, we should get only a straight line. The blue region that region should only be the for me the region of your illumination and a bright spot basically. If I am taking the ray optics into the consideration if the light is traveling in the straight line. But you know that if the wave optics consideration is being taken, when a ray of light is touching the edges, it will be slightly bending in the upward direction, up and as well as of your down. And it is making the small angles and it is making your small angles for the given condition right now, isn't it? So that bending of a ray of light is called as of what? Diffraction. ఇప్పుడు చూడండి diffraction la, if this is your screen right now, if this is your screen and this one is your slit right now, this one is your slit right now, ఇక్కడ నుంచి పడే ray of light ఇట్లా పోతుందా, the ray of light ఇట్లా పడి ఇట్లా పోతుంది diffraction. ఈ రెండింటి మధ్యలో డిస్టెన్స్ సే ఫర్ ఎగ్జాంపుల్ క్యాపిటల్ D అనుకోవచ్చు లేకపోతే Z అని రిప్రజెంట్ చేసుకోండి, ప్రాబ్లం ఏమీ లేదు, డిపెండ్స్ అపాన్. Actually ray optics గనక applicable అయ్యింది, the ray of light will always travels in a straight line and మనకు we should have been got only the bright part in this one. But due to the bending of a ray of light, what is happening? Making a small angle theta. This one is also making a small angle theta. We are getting the light even in the geometrical shadow. Now, if I increase the distance capital D beta, if I increase the distance capital D, and this screen ikkada iskela anukonde right now. Appudu emayipotundi, this bending of a ray of light itla padi itla ayipotundi. Ante almost all it is coming nearer to your bright region. Ante red region ఏదైతే ఉందో అక్కడికి వచ్చేస్తుంది. ఎందుకంటే స్ట్రైట్ లైన్ ఇక్కడ వరకు అయిపోతుంది కదా రైట్ నో, ఇక్కడ వరకు. అంటే బెండింగ్ ఏమైపోయింది, ఇంకా తగ్గింది. And as the distance is been increasing, that is the bending of the ray of light is being overcoming, and that is being becoming negligibly small and small and small, and finally it appears to be straight line. And under that condition, it will act as of your ray optics validity. So that what is telling right now in this one. Okay, proceed this one. What is telling right now there is a parallel beam of a light of wavelength lambda on passing through an aperture, of a size of AD, which gets diffracted into a beam of an angular width theta. Theta ఎంత అవుతుందన్న? Theta is equals to lambda by your D. How do I got that one? From path difference. Delta x is equals to your D into sin theta. Theta very small kabatti. Delta x is equals to D sin theta. From this relation, D sin theta is equals to N into lambda. N is nothing but first minimum మాట్లాడుతున్నాం కాబట్టి 1. Theta is very small, so theta is equals to lambda by D. ఇక్కడ నుంచి వచ్చింది. If the screen is placed at a distance capital D, this beam spread over a linear width అంటే ఇది right now. ఈ linear width అనుకుంటాం. This one is nothing but if your linear width x, or sometimes we also represented by y. ఈ distance ఎంత వచ్చేసి capital D. అంటే tan theta is equals to రాయొచ్చు, theta is equals to y by z అని రాయొచ్చు, లేకపోతే y by d అని రాయొచ్చు. అవునా కదా, tan theta. అవునా కదా. So this one is nothing but from here to here, this distance is right now capital D. This is a linear width, this is nothing but x, and this is making an angle theta. Isn't it? So tan theta is equals to your x by d, x and రాయొచ్చు లేకపోతే y and రాయొచ్చు. That is no problem for me depending upon the given condition. And theta ఎంత వచ్చింది right now for me? Theta is equals to x by d, x by your d part relation. So from that one I am writing right now relation. The beam will spread over a linear width of x is equals to right now how much for me? X is equals to your theta into your capital D. Theta value ఎంత వచ్చిందన్న? Theta value is lambda by small d into capital D. So this is your linear width formula. So that what I got here right now. X is equals to d into lambda by small d. No, linear width ఏమైపోతుంది? That will go on decreases if the distance between the slit and as well as of this d is increasing. The x value goes on, becomes slower, lower, and finally it will become like a straight line. So if the diffraction spread x is very, very small, then the concept of ray optics will be valid. Is that point clear for everyone, beta? Is this point clear for everyone? మరోసారి చెప్పనా? Generally diffraction జరిగేటప్పుడు మనకు ఈ వాల్యూ ఆఫ్ y వస్తుంది. If the screen distance వచ్చాను దూరం తీసుకెళ్ళాను అనుకోండి, ఈ y వాల్యూ ఏమవుతుంది? తగ్గుతుంది. అంటే as the value of y or x is been decreasing, that is appearing to be coming in a straight line కదా. So that will appear as if it is coming in a straight line, but that will be the valid condition for the ray optics, because geometrical optics, light always travels in the straight line assumption if you are taking. Like see, if this distance is very, very small, like say 0.2 mm, 0.1 mm, 0.3 mm, 0.12 mm, 0.13 mm undanukondi. So that is very, very small. Like theta is 1 degree, 2 degree, 3 degree, 4 degree, 5 degree. Within some amount 7 or 8 degree undanukondi. It is very, very small, but that is comparably negligible. So at that time, the diffraction can be neglected and assumed as of your ray optics part affiliation. That's what is telling right now. A parallel beam of a light of wavelength lambda and passing through an aperture of a size d gets diffracted into a beam of your angular width. So that angular width is calculated by the formula theta is equals to lambda by d. If the screen is being placed at a distance of capital D, this beam spreads over a linear width. Linear width and the value of vertical value. And the y and x and rayachu, so that value is equals to d into lambda by small d part affiliation. Now see, if the diffraction spread x is very, very small, then the concept of your ray optics will be valid. Now I could example this one, only for example I have taken. If we have an aperture, small d is equals to, if I am an aperture of small d is equals to 10 mm, and we are using the light of wavelength lambda is equals to 6 into 10 to the power of minus 7 meter, and the beam after traveling a distance at a capital D, 3 meter, will get diffracted through a width formula x is equals to capital D into your lambda into by small d. Capital D is 3 meters. Wavelength is given how much for me beta? 6 into 10 to the power of minus 7 meters divided by d. D is your 10 mm. To convert that one into meters, 10 into 10 to the power of minus 3. And to simplify just 10,000, 18 into 10 to the power of minus 5 meter or 0.18 mm. 0.18 mm, and see how much small it is. Very, 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 very small. So as x is equal to 0.18 mm is not a quite larger, so the ray optics is almost all said to be valid. So we defined here the Fresnel's distance, that if the distance between the screen and as well as of your slit is being comparable in such a way that the light is not bending larger, then that distance is called as of your Fresnel's distance. So the definition I have written, see, the distance at which the diffraction spread of a beam is equal to the size of your aperture. The diffraction at which, the distance at which the diffraction spread of the beam is equal to the size of an aperture, that is called as of your Fresnel's distance. That Fresnel's distance is represented by df, or sometimes some books it is also represented by letter z. So there is no difference, or there is no much difference in that one. So Fresnel's distance and in the distance between the slit and as well as the screen at which the diffraction spread of the beam is becoming equal to the size of your aperture, it is called as of your Fresnel's distance. And when x is equals to d, x ante ikkada ee vertical, this y is equals to slit width distance samanamaindanko, then that distance is called as of your Fresnel's distance, ante capital D is called as of your df. Now use this formula, ee formula ne ikkada use chestunnan chudandi. I am using this formula right now. X is equals to d plus df into lambda by small d. D into d, this will become d square, so df will be equal to how much for me? D square by lambda. So that is of your Fresnel's distance formula. So Fresnel's distance formula in manaku df is equals to d square by your lambda, d square by your lambda part of relation. I hope you are clear with this one. Ikkada varaku ardhamaindi andarki? Is it clear up to this point?
Yes, sir.
Chalo. Next condition chundana. If your capital D is lesser than Fresnel's distance, what do you mean by that one? Capital D is nothing but what? Distance between the screen and as well as of your slit. If that distance is lesser than the Fresnel's distance, then there will not be too much of a broadening by diffraction. That means light will be traveling along the straight line, and the concept of the ray optics is valid. Ante ray optics ganaka manaku valid avvalante condition em undala? D must be lesser than of your Fresnel's distance, or the value of your d must be lesser than of this formula what I am writing is lesser than d square by lambda, or d must be greater than of your, if I am just simplifying this relation right now, taking the d value out, so that value I am getting it as d is greater than under root of lambda into d. That is nothing but of your slit width of a distance. That means for a given value of a capital D, the quantity root lambda d is called as of what? Size of your Fresnel zone. Is called as of what? Size of your Fresnel zone, and it is denoted by your df. So df is equals to under root of your lambda into d. Removing the proportionality constant greater eithundo, this is konte df must be equal to under root of your lambda by your d part relation, greater or equal. That means the concept of ray optics can be conveniently used without introducing any error if the size of the aperture is greater than the size of your Fresnel's distance. And your d must be greater than Fresnel's distance. Then the wave optics can be comparable with your ray optics part of relation. Okay, so just overall remember the formula for that. So Fresnel's distance formula is right now for me what right now? DF is equals to D square by lambda, or D must be greater than under root of lambda by U, lambda into D, or DF is equals to under root of lambda into D. Under root of lambda D is called as of what? Size of your Fresnel's zone. Now see this question right now, beta. Light of wavelength 600 nanometer is incident on an aperture of size 2 mm. Calculate the distance up to which the light can travel such that its spread is lesser than the size of aperture. So we got a wavelength of 600 nanometer and it is incident on the aperture of size how much? 2 mm. Now calculate the distance up to which a light can travel such that its spread is lesser than the size of your aperture. So D value is given how much for me? 2 mm. Fresnel's distance formula you already know, DF is equals to your D square by your lambda, D square by your lambda. That means D value is 2 into 10 to the power of minus 3 whole square divided by wavelength is 600 nanometer, 600 into 10 to the power of minus 9. Simplifying it, we are getting 6.67 meters. That means at a distance lesser than 6.67 meter, the spread of the light is lesser than the size of your aperture. That must be the basic condition. The same way, one more question you see right now. For what distance is the ray optics a good approximation? For what distance is the ray optics a good approximation when the aperture is 3 mm wide and the wavelength is 500 nanometer? Can anyone tell me what is the answer for this question, beta? For what distance is the ray optics a good approximation? What distance and Fresnel's distance? DF kavala. So DF value enta manaku? DF is equals to D square by lambda. D value enta ichadu 3 mm. So that will be equal to how much for me? 3 into 10 to the power of minus 3 whole square divided by wavelength. Wavelength enta ichadu 500 nanometer ante 500 into 10 to the power of minus 9. So that is 10 to the power of minus 6, 10 to the power of minus 9. Ikkada 2 kuda vellipotundi. So that will become 3 by 5. Simplified, see how much I am getting roughly? Anyone?
18.
So that will become for me 18 meters. That means for what distance a ray optics is a good approximation means if the Fresnel's distance is right now 18 meter. Fresnel's distance and distance between the slit and as well as of your screen. This distance. If this distance is like of your 18 meters, then the ray of light, whatever it is been falling on that one, that will go in a straight line. That will be obeying the property of your rectilinear propagation of your light. Is that clear for everyone? Is it clear for everyone?
Yes, sir.
Okay, sure. So I hope that is the basic conditions you need to remember for the given condition. How do you calculate the intensities for the given part of relation? Clear for everyone, beta? Sure. Equation answer cheppandi sir. My screen is again getting struck. I don't know when it is going to stop. Till the time you try to listen the lecture. What is the time now? Chalo. Question no. The light of wavelength 600 nanometer the light of wavelength 600 nanometer is incident normally on a slit of width just a minute, I'm on host kada.
Hey, నీ girlfriend ఉందా? Are you sure?
Sure, 100% confident.
ఏంట్రా అది?
మరి ఈవిడెవరు?
హలో
అమ్మాయి ఎవర్రా?
మా పోరియా అది మొన్న
Chalo. The light of wavelength 600 nanometer is incident normally on a slit of width 3 mm. Full stop. Calculate the linear width of central maximum on a screen kept 3 meter away. Kept 3 meter away from the slit. Chalo. Mirandar Jesse, you give me the answer in the chat box. Can anyone give me the answer? Chat box lo answer ivandi. Linear width of central maxima in the diffraction pattern. One student is giving me the answer 600 micrometers. No. 1.2 mm. Very good. Someone has given. Shravyasri. Very good. The light of wavelength 600 nanometer is incident normally on a slit width of 3 mm. Calculate the linear width of central maxima. Linear width of central maxima ante na beta naught kada. Beta naught is equal to how much for me? 2 times of d into lambda by small d. Antena? So that is equals to 2 into capital D given how much for me? 3 into wavelength is equals to 600 into 10 to the power of minus 9 divided by small d. Small d is nothing but of what? Slit width 3 mm. And that will become for me 3 into 10 to the power of minus 3. So simplify it, you will get the answer for that one. This 3 gets cancelled to 6 are 12. So that will become for me 1.2 into 10 to the power of minus 3 meter. Antena? And that will become for me how much? 1.2 mm. Clear? Is it clear for everyone?
Yes, sir.
Sure. One more question. A 0.02 centimeter wide slit is illuminated at normal incidence. At normal incidence of light of wavelength 6000 angstroms. Stop number 1. Find the width of central maximum. Find the width of central maximum band. On screen placed 1 meter placed 1 meter away from the slit. Under pen paper is going to try shade question number 1. Question number 2. What should be the fringe width? What should be fringe width if the apparatus is immersed? If apparatus is immersed in water, whose refractive index is 4/3, whose refractive index is 4/3. Chalo, try to do it out. Let me see how many of you can give me the answer for this one. First one answer in the Nana. .2 centimeter wide slit is illuminated at a normal incidence of a light of wavelength 6000 angstrom. Find the width of central maximum band on the screen placed 1 meter away from the slit. .6, very good. Shravyasri. Vedamsha Bode, 1.6 mm indukra. Again, you are using the small, wrong formula. Central width in the formula cheppanu. Beta naught is equals to 2 times of d into lambda by small d. So that is equals to 2, kept a distance of 1 meter. Wavelength is given as 6000 angstroms and 6000 into 10 to the power of minus 10 meters divided by small d. Small d is 0.02 and this will become for me 0.02 into centimeter kabatti 10 to the power of minus 2. So then chain ento vastundi powers vellipotayi e2 r2 vellipotundi 3 e2 10 to the power of minus 10, so it will become 10 to the power of 12. This is 10 to the power of 13, sorry 12, 13, 14, 15. This will go off right now, so this will come for me how much chudandi 2 divided by this one to 10 to the power of minus 10 kadadi. So minus 10 and this will become for me plus, that will become 8, 8 nunchi malla 3 vellipotundi. So that will come for me power 10 to the power of minus 3. So this will be 6, yeah. So it is 6 into 10 to the power of minus 3 meters. So that will become for me 0.6 centimeters. Clear? So the width of the central maximum band on the screen placed 1 meter away from the slit is 0.6 centimeters. Second question. Din tarvata resolving powers undana. Resolving powers, I'll try to do it when we do the optical instruments. In the ray optics, we have been left out with the optical instruments, like what do you mean by the lens of your microscope, telescopes, and astronomical telescopes part deflation. In that one, we'll try to do the resolving power. So if you get any problems related to resolving power right now, we keep them to the hold, because that we'll try to do once we complete in the ray optics the optical instruments. Okay, so 4 students are giving me the answer. 0.45 centimeters. Very good. Shravya Sri is giving me the answer 0.45. Calculation mistake, sir. Vedam. Sorry, sir. Calculation mistake. Very good. Okay. Small calculation. MPC students, mere calculation mistake cheste etla cheppandi. Okay. What should be fringe width if it is immersed in the water? You know that when it is immersed in the water, fringe width will become for me how much beta? Beta naught dash will become for me d into lambda dash divided by small d. When apparatus is immersed in the water, fringe width will become how much? What should be fringe width? Appearance has been immersed in the water. Central anala. Fringe width another. Fringe width it may be the first or it may be anything. So it is d lambda ante, that is nothing but d. Lambda dash value will be equal to how much better? Lambda dash is equals to lambda by mu. And already మీకు దాంట్లో చెప్పాను. Wavelength ఎంత ఇచ్చాడు మనకు problem లో? Lambda dash, it is d into lambda dash is nothing but of your lambda by mu into d. అవునా కదా? So d by lambda is nothing but half of this one. అవునా కదా? సో దట్ విల్ బికమ్ ఫర్ మీ హౌ మచ్ 2a కదా, సారీ సెంట్రల్ ఏం అనలేదు కాబట్టి I'll take the same thing. So it is 2d into lambda by, so this is also 2, yeah, 2d into your lambda dash, so it is 2d lambda by d value is how much for me, 0.6. So that will become for me 0.6 divided by refractive index is 4 by 3. So this will become for me 0.6 into 3 divided by 4. 6 by 10, 6 3 is 18, 18 by 4. This will comes around for me 0.45 centimeters. What should be the fringe width if apparatus is immersed in the water? And the central frame maxima గురించి మాట్లాడుతున్నాం. So beta naught dash is equals to 2 into lambda dash. ఇది minus కాదు, this is equals to 2d into lambda dash by small d. So it is 2d lambda by mu into d. So 2d lambda by mu value already we got it as of your 0.6. So 0.6 divided by 4 by 3, it is 0.45 centimeters. Clear for everyone? 0.225. ఎందుకురా? d lambda by d is a fringe width అంటే వాడు డార్క్ బ్రైట్ అని ఏం చెప్పలేదు కదా. సో వీఆర్ ఇమ్మర్సింగ్ ద సేమ్ YDSC విత్ సెంట్రల్ ఇన్ ద వాటర్. అప్పుడు ఏమైపోతుంది, వేవ్ లెంత్ ఒకటే మారుతుంది. బీటా నాట్ డాష్ ఈజ్ ఈక్వల్స్ టు 2d ఇంటూ లాంబ్డా డాష్ బై స్మాల్ d. ఆ ఫ్రింజ్ విడ్త్ నువ్వు YDSC తీసుకుంటున్నావు 0.255 రావడానికి వేదం. ఓకే నా చలో, ఓకే సార్ అంట, వెరీ గుడ్. चलो
सर
यस बेटा,
ये क्लास कब स्टार्ट हुई थी?
5:30 बेटा.
ओके सर.
क्यों?
नहीं मैं अभी आया, फोकस में हूँ मैं.
अच्छा फोकस से हो आप? नहीं अभी तो स्टार्ट हो गई, एंडिंग में है. कैसे भी रिकॉर्डिंग है ना बेटा, आपको डाउनलोड कर देता हूँ, आप देख लो.
यस सर.
This is an IIT JEE advanced question beta. In 2016 it is asked, but even NEET students can try this question. Okay, question is lengthy, but it's really very easy, but understanding is very much important. So see the question, what exactly says. We got an angular width of central maxima in front of a diffraction pattern. In front of a diffraction pattern. Front of a diffraction pattern of a slit is measured. First off, the slit is illuminated. The slit is illuminated by light of wavelength by light of wavelength 6000 angstroms. When slit is illuminated by light, when slit is illuminated by light of another wavelength, the angular width decreases by 30%. Calculate the wavelength of this light. Calculate the wavelength of this light. Stop. The same decrease in angular width in the angular width of central maximum is obtained when the original apparatus is immersed in a liquid. Find the refractive index of liquid. Find the refractive index of liquid. Question is lengthy, but working is very easy. Please try to read the question carefully before you try to attempt it. That is very important. Understanding the question is very important for us. We got an angular width of central maxima in a Fraunhofer diffraction pattern of a slit is being measured. The slit is illuminated by light of wavelength. How much for me? 6000 angstroms. Okay, wavelength is given as 6000 angstroms. That is the first data. When slit is illuminated by light of another wavelength like lambda dash, the angular width decreases by, that means theta dash decreases by 30%. That's what he is telling. Calculate the wavelength of the light. Can you do this one? In single slit, Fraunhofer diffraction at a single slit, the d sin theta is equals to n lambda. Lambda is nothing but 1. So sin theta, n is equals to 1, sorry. Sin theta is equals to how much for me? Lambda by t. As wavelength is very much lesser than d. Wavelength is nothing but how much for me? 6000 angstroms. And the vertical, that small d is given how much for me right now in the problem C? Fraunhofer diffraction. So slit is illuminated by light of your wavelength. The angular width of that one is 30% right now. So the same decreases, so 30%. The wavelength of the light will be equal to how much? That means wavelength of the light, whichever you are using the diffraction, is much lesser than the slit width. Then we can write sin theta is equals to how much for me? Theta. So theta is equals to lambda by d. This approximation direct was coach. Okay now. So now, what is an angular width of the central maxima beta? 2 theta. So 2 theta is nothing but what for me? 2 into lambda by your small d. So I can write from this one. This is angular width. That angular width I am representing it by 5. So 5 is equals to 2 lambda by d. 2 by d is constant. So 5 is directly proportional to wavelength. 5 is nothing but what? Angular width. Angular width. So I can write here phi 1 divided by phi 2 is equals to lambda 1 by over lambda 2. We need to calculate lambda 2. So lambda 2 is equals to phi 2 divided by phi 1 into wavelength, that is nothing but lambda 1. Phi 2 is how much beta? 70% decrease. Ante, sorry, 30% decrease and the remaining is how much? 70%. And 70 by over 100. Phi 2 is so 30% decreasing of phi 1. Phi 1 gets cancelled. So remaining is 70%. So 70 by over 100 into wavelength is 6000 angstroms. So this 2 zeros will get cancelled. 7 6 are. So this will become for me 4200 angstroms. So this is your lambda. Very easy, kada? Isn't it? I hope you got this point right now. I got phi 2 is equals to 30% decrease and it is 70% of phi 1 and Ardham Nana. I hope this statement is clear for everyone. Okay, na? 30% decrease or not? 30% decrease and remaining in the 70%. That is this what I'm idea on all basically. Clear for everyone? So now when apparatus is immersed in the water, now how do you calculate the refractive index, beta? Number B. When immersed in water, how do you calculate the refractive index? Mu is equals to lambda by wavelength in water. That is nothing but lambda dash. Wavelength is how much? Original wavelength is 6000. Lambda dash is 4200. You got it now? So this two and this two will get cancelled. So it is 60 by 42. So how much it is I'm getting, beta? 1 la bothunga tha. So it is 1 point, so 4, 1.43, yeah, 1.43. So that will be the refractive index. Vachinda andarki? Is it clear, beta? When it is immersed in the water, refractive index is calculated with the formula mu is equals to lambda by lambda dash. Okay now? No answer, no response.
Yes, sir.
Clear, sir.
So by this we have been completed your diffraction beta. In the tomorrow session of a class, we'll be starting with your polarization. I'm writing a little bit slower on the my tab because it is getting stuck and it is getting stopped. That is the reason I'm not able to exert a lot of pressure. I need to show it for some technical problems. So please try to bear till that time. I don't know if I give this laptop, it will not come for 2-3 days. Then I can't even take the class for 2-3 days. So that is the reason I'm trying to write it very slowly on the board. So try to go through today the topic of your diffraction, and tomorrow session we'll try to start with your polarization, and in this week we'll try to keep the full stop for your wave optics. And I'm telling you once again, the resolving power of microscope and telescopes, we will try to do it after we do the optical instruments of your ray optics. I kept the topic there hold. So once I do the topic, then we'll try to come back to the resolving power and also the Doppler effect in light, because the students are right now doing the wave optics. Those who are doing the wave optics, once you complete your Doppler effect, you let me know in your waves per chapter. Then we'll try to do the Doppler effect in your light. Otherwise, you can directly ask your running teacher who is teaching the waves. There itself, the sir may also help you out when he is teaching the Doppler effect in the waves. So he can also do the Doppler effect of the light, red shift, blue shift, అవన్నీ కూడా మీకు wave optics లోనే సార్ చెప్పుకోవచ్చు most probably. If he is not telling you, please let me know. I'll try to include that one in my extra class of your optical instruments as per the situation. Okay now? In exam time doubts unte, please let me know beta. Any questions if you can share with me. I've not even seen the question paper. Actually, I thought the question paper which was given by me they kept, but unfortunately they kept some other paper which even I have not seen it. So if anyone can share me that questions, the questions which you couldn't able to do, I can help you out. So I hope everyone is clear with your YDSC, all the cases, diffraction phenomenon. So almost like 13 or 14 lectures have been completed. Another 8 lectures will go for the polarization beta. What is today? Today is Monday, Tuesday, na? So Wednesday, Thursday, Friday, Saturday. So another 4 lectures I'll try to do polarization. Monday and Tuesday also I'll try to do. So overall we'll be having 20 lectures of your wave optics on your YouTube. You can see it regularly and try to do. And on 1 or 2 sessions will be exclusively for the numericals of NTA. This year NTA has released some 80 to 100 NTA question papers. So we are getting one question in each of the papers. So roughly we'll be getting some around 70 or 80 questions. Whichever questions I can collect it, and I'll try to share with you. Let's see how far you can do it out basically. Okay now. So once this has been completed, I'll try to do some good questions of your NDA exam, both which is applicable for the NEET and as well as of your JEE mains. Okay. So this is your ending of your diffraction. We'll try to start with the polarization in the next session of your class. Let me see any good question I'm having with me so that I can share with you now. Let me check with this one. Diffraction, all small questions only. Okay, take this question as an homework beta. Very good question. Lens of focal length 1 meter. My goodness, 1 meter. 1 meter forms Fraunhofer diffraction. forms Fraunhofer diffraction. Fraunhofer diffraction pattern of a single slit of width 0.04 centimeter 0.04 centimeter in its focal plane. So this is something new framing. So the incident light contains two wavelengths, lambda 1 and lambda 2. It is found that the fourth minimum corresponding to lambda 1 and the fifth minimum corresponding to lambda 2 occur at the same point 0.5 centimeter from the central maximum. Okay. Compute lambda 1 and lambda 2. That means calculate me the value of your lambda 1 and as well as of your lambda 2. Can anyone try it? Length of focal length is given how much for me, beta? 1 meter. Forms a Fraunhofer diffraction pattern of a single slit of a width 0.04 centimeter in its focal plane. The incident light contains two wavelengths, lambda 1 and lambda 2. It is found that fourth minima corresponding to lambda 1 and the fifth minima corresponding to lambda 2 occur at the same point, 0.5 meter from the central maximum. Now calculate the values of your lambda 1 and lambda 2. Minima annadu kabatti, what is the position for your nth minima, beta? Can anyone tell me? A sin theta must be equal to n into lambda, isn't it? So if I am writing for this one for the two cases, isn't it? So that is A into sin theta 1 is corresponding to 4 times of lambda 1 and A into your sin theta 2 is corresponding to your fifth lambda. And here theta 1 will be equal to theta 2. That is nothing but some theta because they are coinciding kabatti. That means A sin theta is equals to your this one kabatti. That will become for me 4 lambda 1 is equals to 5 lambda 2. Isn't it? So that is the equation what I am getting right now. Relation between the lambda 1 and lambda 2. So 4 times of lambda 1 is equals to 5 times of lambda 2 part of a relation. Now you know the value for the theta. Theta is equals to what for me? Y. Focal length D will become how much right now here? F, focal plane, isn't it? Because in the YDSC, if this is your slit and this is your screen, so this ray of light when it is been incidenting right now, this will be incidenting and this will be forming right now. So this is very near, means this is almost all very nearer to the slit. This distance I am taking it as of your focal plane F. So this capital D will be equal to your F. That means if this is your D and this is your Y and this is making an angle theta, so tan theta will be equal to Y by D. Theta is very small kabatti, theta is equals to Y by D. This D is equals to your how much for me? Focal plane. So it is Y by your F. That is the reason I have written that one. So theta is equals to Y by F. F is what? Focal length of the lens. Y value is given in the problem how much? 0.05 centimeters. Sorry, this is given as 0.5 centimeters. That is approximately 5 into 10 to the power of minus 3 meters. And focal length is given for me how much? 1 meter. So I can get the value of theta. So theta is equals to 5 into 10 to the power of minus 3 divided by focal plane is 1. So obviously this one will become in terms of radians. So it is 0.005. Unit will be radians because theta covered. Now I can calculate the lambda 1 beta. Therefore, lambda 1 is equals to A into theta divided by 4. Antena? So that is equals to 0.04 into 10 to the power of minus 2 into theta value is 0.005 divided by your 4. You simplify it, we'll get the answer for this one. Similarly, lambda 2. Lambda 2 is equals to your, I can write this one as of your equal to how much for me? Lambda 2 is equals to, lambda 2 from that one I can write 4 times of lambda 1 divided by 5 directly. So it is lambda 1 I got already from the given relation. So it is 4 by 5 into lambda 1. Whatever I'll be getting. So the 4 this one was 0.01. 0.01 into 10 to the power of, until this will become for me 5 into 10 to the power of minus 7 meters. And in nanometers raste 500 nanometers. This will be 500. This will become for me 400 nanometers. 5 ones 5. 400 nanometers. So lambda 1 is 500 nanometers and lambda 2 is equals to 400 nanometers. Is it clear for everyone? Okay now? Chappare? Unnara vellipoyaru andaru? Are you there? No one is responding.
Yes, sir. Yes, sir.
The problem అర్థమైందా మరోసారి చెప్పనా చూడండి. A lens of the focal length 1 meter forms a front of a diffraction pattern of a single slit of a width 0.04 centimeter. Okay, its focal plane is given. The incident light contains two wavelengths, lambda 1 and lambda 2. It is found that the fourth minima is corresponding to lambda 1 and the fifth minima is corresponding to lambda 2 occurs at the same point 0.5 centimeter from the central maximum. Compute the lambda 1 and lambda 2 part of relation. I hope you got an idea. Minima annadu kabatti nth minima is equal to a sin theta into your n lambda. Okay, so one is 4, another is 5. Theta is very, very small. So theta 1 and theta 2 are same because they are coinciding. So we are getting the relation between them as 4 lambda 1 is equals to 5 lambda 2. Then what is the value of theta? Theta is y by d. D is here focal length. That is nothing but f. So y is given as 0.5 centimeters. Convert that one into meters. Focal length is given. So I got the theta. So once I get the value of theta, I can calculate the value of lambda 1. This value I am taking right now. Theta is very small kabatti. So theta is very small kabatti. What I am writing this one is a into theta 1 is equals to 4 times of lambda 1. So lambda 1 is equals to how much for me? A into theta by 4. Theta 1 theta 2 are same kabatti. That will become for me theta. So theta value ochindi, a value is given, 4 is also done. Let's simplify it, we'll get that one. So once you know that one, then use this relation, we'll get the value of your lambda. Clear for everyone? Chalo. I'm stopping the lecture right now. So we'll come back and meet in the tomorrow with a new topic, that is polarization. And already in your WhatsApp group, I have sent you the slides basically related to your wave optics and ray optics. So please try to go through it, everything in the YDSC and the diffraction. Tomorrow session of a class, I'll start with your polarization. Take care, beta. Bye.